Hi everyone. So since I discovered in lecture that many of you have maybe not a strong enough background in your understanding of orbitals and hybrid orbitals and molecular orbitals and how all those things work, I promised you I would give you some supplementary information on that. So I'm doing a video now where I can go through that stuff with you. So I'm going to review all that stuff that you need to know for 14D. So I'm not necessarily going to test you on this stuff explicitly, but an understanding of atomic and molecular orbitals and what they look like, they're going to serve as an explanation for why certain reactions give the products they do, or why they have certain requirements that they do, and why they give the outcomes that they do. All of that stuff, or I should say, a lot of that stuff can be explained using molecular orbital theory and looking at the arrangement of those orbitals. All of that, it can really give you a nice explanation for why we observe what we do. And so it's just important that you kind of can understand this to the extent that you can make sense of those explanations as we move forward. So we're going to use those explanations as it pertains to substitution reactions that we're going to look at, also elimination reactions when we get there. And there's going to be a number of other places where we see these kinds of explanations. So I think just a general understanding of this can be really, really useful for making sense of that stuff. So let's start from the beginning. The structure of atoms. We've got our nucleus, which has protons and neutrons. That's in the center. And then we are surrounded by electrons. And those electrons are usually described as being in orbitals. So the way we look at these orbitals, we've got different orbital shapes that we can have. We have S, P, D, and F orbitals. I'm not going to look at the D and F orbitals. Those would pertain to elements that are in the D block or the F block. We're definitely not going to see any of those. Well, I shouldn't say that. We will see things that have D block electrons, but they're not going to be the ones that we're typically going to use for any of these explanations. Most of the times we're going to be looking at the orbitals as they pertain to second row elements. And so because the second row elements don't go beyond the P block in terms of their core electrons or even valence electrons, we don't really need to worry about what those orbitals look like. We will, of course, use elements in our molecules that have d electrons, things like, bromine or things lower on this periodic table, but we're not going to need to draw any orbitals for them. So that's why we're going to stick with S and P. So that'll make this first part pretty simple. So we have an S orbital. Over here is our S block of the periodic table. Over here is the P block. So the shape of an s orbital is spherical in nature. So I am going to, I'll use that same color. The reason the s orbital is spherical is because, and I know I'm depicting this in 2D, but you have to imagine it as being a spherical shape. It's spherical in shape because that is the optimal place where you could put electrons so that they can be as close as possible to the nucleus. So I'm usually going to draw this nucleus using the green marker just so you'll know what it is every time I use it, just to make it a little easier to recognize. So we have our nucleus in the center here, and the closest we can get those electrons in that orbital would be to have a spherical distribution around that nucleus. And since the s electrons are the first thing as we build out, right, because we're going to keep adding electrons as you start from hydrogen, and then you move over, we're going to keep going here and then coming back to the next row and the next row, because it's the first electron, or the first set of electrons you put as you build electrons up in any atom. Then the first electrons you place there are going to want to be in the most optimal position relative to the nucleus. When you have to add more electrons, it's going to be a little less optimal, but it's going to be basically now the closest we can get, but not overlapping with what we have in the s orbital, and they're just going to keep building out from there. So we're always going to give it the best possible position, but not overlapping with another orbital. Okay, so we start off with S, spherically shaped around the nucleus. Then we go to the P block. So the P block needs to accommodate 6 electrons. 1, 2, 3, 4, 5, and 6. The S block has already accommodated for 2 on its own, 1 and 2. So I'll go ahead and fill those in down here. Each orbital can hold exactly 2 electrons with opposite spins, and then from there you need to go to another orbital. And the orbitals, for the most part, aren't going to overlap with one another because the electrons, when you have electrons in those orbitals, the electrons in adjacent orbitals are, because they're both negatively charged, they're going to want to repel one another. So you want to keep them as far apart as possible, but still be as close to the nucleus as possible, of course. Okay, so we have 6 electrons in the p block, and that's why we have 3 different p orbitals. So we have, we can put 2 electrons in the px, 2 in the py, and 2 in the pz. So with s orbitals, they're spherical in shape. So you couldn't have something like s, x, y, or z because the spherical shape doesn't lend itself to a directionality. Whereas the p orbitals, on the other hand, which are shaped sort of like dumbbells, remind ourselves where the nucleus is every time. Here we can have this in 3 different orientations. Let me just, so they go in order, do it in the order of px, py, and pz. So here is my px, then I'm going to have py, and then pz is going to be a little more difficult to show, but I'll just kind of draw it going out like this. So you have to imagine that that this back lobe here is going back into the plane of the paper, and this one's coming out at us in that z axis. So here we have px, py, and pz. And so again, because electrons in one orbital compared to another, being both negatively charged, are going to repel each other, you want these orbitals to be and having them all orthogonal to one another, px, py, and pz is the best way to situate those. And we have our nucleus here. And you'll notice that px, py, and pz, they're not going to overlap one another at all. And even if we superimpose them onto the s orbital, you can see, probably should have made the p orbital a little bit bigger, but there's very minimal overlap. And in fact, when you do have some overlap with the s orbital, you can see that's when the shape of it sort of shrinks down. So in this way, these orbitals, or these pairs of electrons in the orbitals, aren't overlapping with one another. Okay, and then as you go down to another row, right, so if you go here from the 1s down to the 2s, now these orbitals are going to sort of build out this direction. Okay, so that covers the basics of the atomic orbitals, at least for atoms that we'll see. And now I'm going to talk a little bit more about how we can use these orbitals to depict molecular structure. So in general, there are 2 main ways that we use to predict or depict, maybe envision, I guess, molecular structure. The 2 common ways that we use are valence bond theory . And this is one that you're very familiar with, even if not by name. And the other main one is molecular orbital theory, or MO theory. So valence bond theory is what we do when we draw Lewis structures. When we draw Lewis structures and we predict molecular geometry based on the steric number. So what valence bond theory does is it considers bonds as the electrons of bonds as localized between a pair of atoms. So you create bonds from overlapping either atomic orbitals or hybrid orbitals, and we use them to form either sigma or pi bonds. So what we can do then is by looking at that, we can predict the molecular shape based on the number of pairs of electrons that we have to space out. So let me just give a quick example of that. If we look at water, to show you how you've already used valence bond theory, we draw the Lewis structure first. And then we look at this and we state the steric number. So if I want to look at the molecular geometry, then I want to focus in on the central atom and look at how the outer atoms are arranged about that central atom. So we look at oxygen and we can calculate what's called the steric number. Not really a calculation, it's just counting. So the steric number is basically looking at how many orbitals need to be spaced apart. So what you look for in steric number is to look at how many atoms are around the central atom and how many lone pairs. So here we have 1 lone pair, 2 lone pair, an atom, and another atom. So that's 1, 2, 3, 4. So the reason I'm circling the atoms rather than the bonds, which kind of looks like it might make more sense, is because you could incorrectly calculate the steric number if you were counting it by bonds. And I'll give you an example of that right now, actually. So let's look at carbon dioxide. So carbon dioxide, the steric number is actually 2. So we are counting lone pairs. Carbon has 0 lone pairs on it. and then we're counting surrounding atoms or bonded atoms, not number of bonds, but bonded atoms. Here, the central atom carbon is bonded to oxygen and oxygen. So the steric number here is actually 2, not 4. And the whole purpose of why we're counting it this way is we want to know basically how many things we need to space apart, because these bonds are going to contain orbitals, which contain electrons, which are going to repel one another. So the reason we count bonded atoms rather than bonds is if we have something like a pi bond, I've got sigma bonding electrons and then I've got pi bonding electrons, but I can't separate those out, right? They're both serving to bond the carbon and oxygen to one another. So they kind of go together. Whatever they're going to do together. If I would move it up here, move it down here, they've got to work in sync with one another. They're a bonded system. A sigma bond or a pi bond, all of that is one bonded system, no matter how many are there. So that's why we don't count that as 2 on one side. We count the oxygen on each side as 1. No matter how many times it's bonded to the central atom, whether it's 1 bond or triple bond, double bond, doesn't matter. Okay, so let's see here. And the reason we like to calculate this steric number is it gives us 2 other pieces of information. One is the geometry about the central atom. The other one is the orbital hybridization. So the geometry about the central atom. So let's take a look at the one on the left. The steric number here we said is 4. That means there are sort of 4 different entities that it wants to space apart to avoid those, because those electrons in those systems are going to repel one another. So the best way you can space apart 4 things, that meaning the bonded hydrogen, the other bonded hydrogen, and each one of the lone pairs, when you have a steric number of 4, so 4 things you want to space apart, the optimal distance between those things would give you what's called a tetrahedral arrangement. So that's where you have, I'm just going to do this generically with little circles. I'll fill them in so they don't look like oxygen atoms. So you have this central atom right here. Circle that in pink so it looks a little different. So you have these 2 pointed slightly down off to the right and off to the left. And then basically what you have is something sort of coming forward out at us. And then we have this other one going back into the plane like this. So that's our tetrahedral structure that separates all of these bonds by bond angles of 109.5 approximately. And then, so that's sort of its parent structure. And because for molecular geometry, we basically only want to know about the arrangement of atoms about the central atom, then we basically say, well, okay, this one is a lone pair of electrons, and this one's a lone pair. So the net result, or the molecular geometry that's left over, those lone pairs are still there. They still affect the parent geometry, which in turn affects the molecular geometry. Because when we look at molecular geometry, we're not changing anything or removing the lone pairs. We're simply ignoring them in our assessment of geometry. So when we look at only the atom portions of that, you can see it gives what's referred to as a bent structure. So it's a bent molecular geometry with bond angles of 109.5, or approximately that. So now if we look at carbon dioxide, which has a steric number of 2, it now only has these 2 bonded oxygens it's trying to space apart. And again, because we can't sever the sigma bond from the pi bond, if we did that, we would just have 2 sigma bonds. Then we just have 2 pi bonded oxygens that we're trying to space apart. That tells us that the steric number is 2, and that the molecular geometry is therefore linear, because in the case where we only have 2 things we're supposed to space apart, the best way to keep them far apart from one another is to have them pointed in completely opposite directions, so separated by 180 degree bond angles. Okay, let's see, what else do we want to say here? I'm also going to give the table of hybridizations, but I think I'll save, I'm going to talk about hybridization of orbitals down here. So we are going to look at that in just a minute. So right now, I'll just give you a little table off to the right of how you use steric number to predict hybridization. So we're only going to look up to a steric number of 4 just because we're not going to really see that beyond that. We do have examples beyond that and what their hybridizations are, but we're not going to use that day to day. So let's use steric number 4, 3, and 2. If you had a steric number of 1, you wouldn't really have a molecular geometry, so you'll probably just be looking at a pure orbital. Anyway, steric number 4, 3, and 2. For a steric number of 4, the hybridization is sp3. For a steric number of 3, the hybridization is sp2. And for the steric number of 2, our hybridization will be sp. So I'm going to talk about these hybridizations in much more detail to show you where those hybrid orbitals come from, what they mean, how many of them we have, and why we might leave behind pure p orbitals versus just pure p or s orbitals rather than hybridizing them. So we'll get to all that in just a little bit. So again, that's valence bond theory. That's stuff that I think pretty much everyone seems to understand quite well. So let's move on to molecular orbital theory. So both valence bond theory and molecular orbital theory both describe the structure of molecules and the way that they're bonded together. And they're complementary theories. They sometimes one depicts things in a more useful way for whatever you're looking at, and sometimes the other one is a bit of a more useful way. So they give us slightly different perspectives and can be used to complement one another in terms of our understanding of what the structure of molecules is. Okay, so molecular orbital theory. Here what we're going to do is we're going to look at the wave functions of the atomic orbitals and combine those wave functions to provide molecular orbitals. And what that's going to give us is it's going to give us a depiction of these so-called bonding and anti-bonding molecular orbitals. And it's going to give us, like I said, a way of sort of drawing these orbital spaces and giving us a better understanding of, or a different, at least, understanding of what the structure of molecules is. Okay, so let me get into a little bit more about what molecular orbital theory is. So first of all, the electrons in atomic orbitals and molecular orbitals, or electrons in general, remember they have properties of a wave. So we can describe the behavior of these electrons in either of these orbitals by a wave function. And that's what these Greek letters here are. So we have phi here and then psi here. So phi and psi are the wave functions that can be used to describe the behavior of electrons in either atomic or molecular orbitals. And you see up here I have them squared, and that's because the wave function squared gives us the probability of finding an electron in a particular area. And so we can use cartoons to kind of draw these molecular orbitals just in the same way we did these atomic orbitals, or these S and P atomic orbitals up here at the top. We can use these similar cartoons to take these atomic orbitals and draw molecular orbitals that sort of depict what we would be doing with these wave functions. So let's take a look at that. I guess before we do that, which order should we do this in? Actually, let's do molecular orbital theory, or give you an example of molecular orbital theory using simple pure s orbitals, like the bonding in for example, H2 gas. I think that would be a good place to start to kind of show you what molecular orbital theory looks like and what we're going to get out of that. And then we'll move on to the hybridization of orbitals, because we can actually use the hybrid orbitals not only in valence bond theory, but also in molecular orbital theory and how we draw those orbitals out. Okay, so let's go with a simple example of molecular orbital theory. And let's compare it with how we would have done I guess valence bond theory in this case, which will be really simple. So if we look at H2, diatomic hydrogen gas, if we were to use a valence bond model, this would be relatively straightforward. We would count the number of valence electrons of each hydrogen and then come up with a Lewis structure. So H2 has 2 hydrogen atoms. Hydrogen has 1 valence electron. So then our Lewis structure drawing would be really straightforward. We would just take these two, I'm going to draw this one like this, and we would say these 2 electrons can form a bond. So we would draw a structure that looks like this for our Lewis structure, and that would be pretty much the end of it. We wouldn't give a molecular geometry, because you only have 2 elements attached, so it can't be anything more than linear. It's not really technically linear, but it can't take on any other shape. Okay, and we don't have to worry about orbital hybridization in these cases, because each hydrogen has 1 s orbital. There'd be no way to hybridize it anyway. There's only 1 orbital. There's nothing to hybridize with. So that would be pretty much everything for valence bond theory. So let's do the same. Let's do now the molecular orbital theory treatment of H2 as an alternate way to describe its bonding. So this is our valence bond theory description. and then we're going to do our molecular orbital theory description. So molecular orbital theory says that we are going to combine the atomic orbitals, mathematically combine their wave functions to provide a molecular orbital. So let's backtrack just a little bit. We are referring to wave functions because the behavior of electrons, because they have wave-like properties, can be described by a wave function. So if we now just take a very rudimentary treatment of a wave, where we can say, okay, we have a wave that looks like this. So if we have a wave represented by, that wave function, then there are two extremes for how we can combine two wave functions, because we're combining atomic orbitals when we make molecular orbitals. So the two mathematical extremes of combining those two wave functions would be, let me draw another wave right here. Let's draw it in. I'm actually going to draw it right on top of it right now, just because it'll make envisioning this a little bit easier in just a second. Okay, so let's take these two different wave functions, which now I'm just drawing as a wave. So let's say that this is for atom 1, and this one is for atom 2. So the two mathematical extremes of how we could combine these waves would be either in phase or out of phase. So let me take these, I'm just going to copy and paste them. Okay. And I'm drawing this visually as waves because it's a lot harder to envision how to combine actual wave functions. But if you're good with math, it's maybe a preferred way. So let's just take a look at these waves. So again, the mathematical extremes would be to combine these in phase or out of phase. So the in phase combination would basically mean that the wave functions have the same sign and that we are going to constructively interfere them. So the way you would have two waves overlap to give constructive interference would be to place them so that these sort of peaks and valleys are at the exact same positions. So if mathematically I combine it by overlaying them like this, take these and combine them in phase. So if I overlap these waves in phase, what I'm going to get is a combination of these two. I guess I'll just use a third color here. I can use green. That's going to be exactly double the height of the two individually. Oops. Right, so you can kind of see visually if I sum these two up in phase, I'm going to get all those peaks being twice as high or twice as low. If I combine these two waves out of phase, which when looking at a wave visually would be the equivalent of me overlapping them like this. If I overlap them like this, and I actually sum these, if I sum whatever value, so if you consider this to sort of be your 0 point, if I sum this value here with this one here, I'm going to end up here. So at any point along this purple wave, when I sum it with whatever's going on in this pink wave, I end up getting this straight line right in the middle. So that is my out of phase combination. So my out of phase combination would look something like this. So let me go back and separate those. Okay. So mathematically, my out of phase combination looks something like this, just a straight line. Okay, so we're going to do this with actual, drawings of these orbitals in sort of a cartoon diagram. And so we're going to have to be a little more creative in the idea of what this in phase or out of phase combination looks like. But understanding, generally speaking, what we're doing when we combine things in phase and out of phase to get constructive or destructive interference, just using this wave diagram helps us understand what exactly it is we're doing. Okay, so let's take a look at our molecular orbital diagram for H2, and then we can kind of get into this a little bit more. So for H2, the way we do molecular orbital diagrams is we start off by drawing the two atomic orbitals, and we draw sort of an energy level here. We say hydrogen 1s, or just hydrogen S is fine. We know hydrogen has one electron, just like we did when we did the valence bond theory. We can still use that information to know that it has one electron. And then I'm also going to draw hydrogen over here on the right-hand side with its 1s orbital and its one electron that it has in there. Okay, so I have sort of on the outsides of this diagram my two atomic orbitals from each hydrogen of H2. So then what I do is I combine these orbitals into molecular orbitals. So when we combine atomic orbitals into molecular orbitals, what we're doing is we are combining those atomic orbital wave functions. And so and then doing it in phase and out of phase, like I said. So what we do when we combine those in phase and out of phase is we're going to get something down here, which would be called the sigma bonding orbital. So sigma S. The S denotation just mean is sigma bond made out of those S atomic orbitals. We don't actually have to have that there. We're going to form a sigma, which is our single bond, and then we're going to form this so-called sigma star, which is an anti-bonding molecular orbital. So again, that's coming from either the in phase or out of phase linear combination of those atomic orbital wave functions. So when we do a linear combination of the atomic orbital wave functions, we get out of that two molecular orbital wave functions. What that shows us is that the electrons in the sigma bonding orbital, as it turns out, go to a lower energy compared to either of the individual atomic orbitals. So if I just kind of draw a dotted line here, maybe the way people normally depict it looks like this instead. Starting from the hydrogen 1s, the sigma bonding orbital goes lower in energy, and the sigma star anti-bonding orbital goes higher in energy. So I'm going to talk about why that is, and I'll also note that the sigma anti-bonding orbital, this delta E value right here, compared to the delta E from here to here, I'll call this delta E1 and delta E2. Delta E2 is actually slightly larger than delta E1. Not hugely, but the energy by which the antibonding orbital goes up is a little bit greater than the amount that the energy goes down when we go to the sigma bonding orbital. Again, I'll explain why that is. It's a slight difference, but it's significant enough that it does make a difference. Okay, so let's see here. Let's take a look at how visually we can combine these 1s orbitals. We already know what s orbitals look like. They're spherical in shape. So let's draw these cartoon diagrams that I've been drawing in lecture to show the bonding and anti-bonding molecular orbitals starting from atomic orbitals. Okay, so now we're going to show how these can combine either in phase or out of phase to give us these bonding or anti-bonding molecular orbitals. So our two atomic orbitals are shown there at the top. Now I'm going to show the phasing. So we can combine, remember, these things either in phase or out of phase. So oftentimes what people do is they'll shade things to simply show if the sign of the wave function is positive or negative, and therefore if two things are being combined in phase or out of phase, just like we did up here with these generic little wave diagrams here. Okay, so if two things are shaded or if two things are unshaded, that means you're depicting an in-phase combination. And if two things have opposite shading, so one shaded, one not, that's meant to depict an out-of-phase wave function combination. Okay, so what I'm going to do is, just for the purposes of showing some shading, I'm going to shade both of these. So when I shade these and I bring these two orbitals into to overlap with one another, so something like this, I can't make it so that the one nucleus is going to overlap the other nucleus. So let me fill that green nucleus in a little bit better so you can see it. So what's going to happen is we're going to bring these as close together as possible to overlap their orbitals, but to not overlap their nuclei. And so if you bring these close together in space like this and you overlap those wave functions such that they're in phase, what you're going to get is an increase in electron density between those two atoms. Because remember, you're combining their wave functions in phase with one another. So if you're combining those wave functions in phase, just like we saw with the generic wave diagram where the wave got bigger, we're going to see an increase in the probability of finding an electron in that area. So when I combine them in phase, I'm going to move this over here just so I can draw an overall better version of this drawing. We're going to get something like this. accident made it change the color of that. Okay, so we're going to get our 2 nuclei here. And we're going to get something like this for the orbital. So I guess I'll shade this so that you can see this a little bit better. Or shaded, I guess, to look consistent with what's over there. I could have left the whole thing unshaded. So again, the shading is really just to say if they match, you know, they're in phase. If they don't match, they're out of phase. Okay, so now what we see, why does this orbital go lower in energy? And I'm trying to depict actual energy levels here with these drawings, with one being below or above and so on. So here's my hydrogen 1s with 1 electron. Here's my other hydrogen 1s with 1 electron. And then I have my sigma bonding molecular orbital here lower in energy. So why, just based on this drawing, is this one lower in energy? Well, what you'll notice now is that where most of this electron density is, which is right in here, the probability of finding an electron there, if an electron is there, it's now not surrounded by just 1 nucleus, but now by 2 nuclei. And so anytime electrons are closer to the nucleus, that stabilizes them because electrons are negatively charged, the nucleus is positively charged. So that's, if we look at the drawing, it serves as the explanation as to why this sigma bonding orbital goes to a lower energy, why it's more stable. It's more stable because the electrons here, most of the electron density based on the cartoon is between those 2 nuclei, and electrons, when they're between 2 nuclei, are going to be even more stable than when they're just next to 1. Okay, so now let's look at the antibonding orbital. So the antibonding orbital would be when we combine these two, now when they're out of phase. So now I'm going to shade one of them, but not the other. And again, I just want to keep reiterating that shading is really just a way of saying, oh, I'm combining these either in phase or out of phase. I could have left these two down here, both unshaded. That still would have been in phase. Okay, so now I'm going to combine them out of phase. So now when I kind of think about bringing these two opposite sign wave functions into contact with one another. Remember, that's going to be the equivalent of an out-of-phase combination, which is kind of like when I overlap these waves like this. So now every place they're overlapping, they're sort of canceling one another. So that's destructive interference. So that's what we're going to show here. So when we do that to these these two things that are out of phase, you can imagine as you start to overlap them with one another, they start to cancel each other out. Right? As I move it in, these wave functions, as they destructively interfere, are going to keep canceling each other out, which means that the portion that we get that's overlapping right here, because they're combining out of phase, they're destructively interfering with one another and basically canceling each other out. Whereas out here in this area, they're not going to cancel because they're not overlapping with the orbital of a different sign. Okay, so let's kind of depict the combination of that, what that would look like. So I'm going to kind of borrow from this one here, just to have those nuclei be the same distance apart. I guess I could have just done that like this. Okay. So the out of phase combination is going to look something like this. There we go. Something along those lines. I'm not a perfect artist here, but now it's going to look something like this. Okay, and I guess I can include the shading if you want that, just to be consistent with what I had over here. Okay, so now I have something that looks like this. Let me move this up just a little bit. I'm going to do the same thing here. I label this sigma star, the star meaning antibonding orbital. And now I want to talk about what I was saying earlier, which is why is the decrease in energy here slightly less than the increase in energy to the antibonding orbital? Okay, well, let's take a look at that. So why do we go up in energy at all? We go up in energy now because we have a larger average distance between the nucleus and the electrons, or the place where we're likely to find an electron, compared to what we had down here with the hydrogen 1s orbitals. So here we can see that the distance from the nucleus to the electrons is this, and now we have an average distance to the electrons, which is farther away in this antibonding orbital. So it turns out that is it has a slightly larger impact in terms of the quantity of that delta E than we do with the bringing them into combination for the bottom. So the sigma star is just slightly higher in the energy, the absolute value of the energy that it goes up than it is when it goes down. So now not only is it not surrounded by two nuclei, it's only surrounded by one, and on average the electrons are farther away from that nucleus compared to what they were in the pure atomic orbitals. Okay, so that is that. Now let's talk about what happens when we put electrons in these orbitals. Oops, I didn't want shading there. So when we put electrons in these orbitals, we're going to start down here. We're going to fill up the atomic orbital, the molecular orbitals based on what we see in the atomic orbital. So we have a total of 2 electrons in the atomic orbitals. So then we start filling the middle of the diagram here, which is our molecular orbitals. So we leave these alone. These are really, you don't even need these technically in the diagram. Sometimes they can make for a more complete looking diagram, but the molecular orbitals are only the ones down the middle here. The sigma, sigma star, we can also have pi and pi star. Okay, anyway, so we have 2 electrons to fill. So as we normally fill electron configurations, we start at the lowest possible energy orbitals, and when those are full, we go up to the next level and so on. So we have a total of 2 electrons, which means we can put both of them into this sigma bonding orbital. Okay, so if we were to put electrons up here, let's just look at that scenario. If I were to put 2 electrons here, now let's look at what's happened. Does it want to still form a bond between these things? So I think just like generically we can say, oh, why would we call this an anti-bonding orbital, and why do we call this bonding? Well, remember, the bonding is the sharing of electrons between 2 atoms. The best place to put electrons if you want to share them between the 2 atoms is between the nuclei, right? And so in the bonding orbital, you can see most of the electron density is between the nuclei, but in this anti-bonding orbital, there's no electron or very little electron density between the 2 nuclei. And so that's why it's called anti-bonding. It does nothing to help bonding. Now, you might say, okay, well, what if there are equal amounts of electrons in each, then it could still have a bond. It would sort of be neutral. But remember that the amount of energy that the anti-bonding molecular orbital goes up relative to the atomic orbitals is a little bit larger than the energy that it goes down in the bonding molecular orbitals. And so for that reason, as soon as you have an equal number of electrons in the bonding and anti-bonding orbitals, you're no longer going to have a bond. That bond is not going to exist, or if you add them in to something that didn't have them before, it would break that bond. And again, that's because this delta E here is just slightly larger than the one on the bottom. So when you have an equal number of electrons in both, you're not going to have a bond. So this can be used to calculate bond order, which is just another way of saying single bond, double bond, triple bond. But you don't always get even numbers. You can get a bond order of 1.5 for certain molecules. Not things that we'll look at, but you can get those. So the bond order is calculated by doing the number of sigma electrons, so the number of electrons in the bonding orbitals. I guess it doesn't have to be a sigma bond. So let's just say electrons in bonding orbitals minus the electrons in anti-bonding orbitals. And then that divided by 2. It's divided by 2 because there are 2 electrons in a bond. And so if we're counting, single electrons up here, and then we want to see what that amounts to as far as a bond, we divide it by 2. So if we look at the hydrogen 1s before I added these electrons, we would have gotten 2 electrons in the bonding orbital minus 0 in the anti-bonding divided by 2. It gives us a bond order of 1. And that's consistent with what we got from valence bond theory somewhere over here, certainly in a much, much simpler fashion, but we arrived at the same answer. And then if you do the diagram for something like He2, so diatomic helium, which you probably know doesn't actually exist. Helium's a noble gas, doesn't want to form bonds. But these orbital diagrams can nicely explain why that would be, which is that if we were looking at helium, there would be an additional electron here and here, which means when we go to fill up the molecular orbitals in the middle, we would also have 2 electrons here. Then we would have 2 electrons in bonding, 2 in anti-bonding. That would give us 0, so 0 divided by 2 is 0. So you might be looking at this and going, why on earth would I use this when I could have drawn H2 using Lewis structures and valence bond theory much more rapidly? Well, it helps us describe a lot of different depictions. These antibonding orbitals, as it turns out, is going to be very useful for us in describing how reactions work and why they give the products they give. But it can also be useful for, we're not going to use it here for this, but describing things like the bonding in oxygen. So if you were to draw a Lewis structure for oxygen, you would draw something that looks like this using valence bond theory. But the real structure of oxygen actually has unpaired electrons, and that's not what you would predict from valence bond theory. And so it's molecular orbital theory that actually allows us to predict why the structure of oxygen is what it is. So on occasion, they give us information that isn't consistent with one another, but one is, of course, going to be more consistent with what we observe in the lab. But oftentimes, they give us information that's consistent, but with a different perspective. And so that's the part that we're really going to use here in organic chemistry. Okay. So that shows you how to overlap atomic orbitals sort of in a cartoon fashion for something simple like hydrogen and create either bonding or anti-bonding molecular orbitals as a result. We can do these drawings or these molecular orbital diagrams and molecular orbital cartoon drawings using pure orbitals like s and p orbitals, but also with hybrid orbitals. And then hybrid orbitals are also used in valence bond theory. In fact, one of the things we calculated here or made a note of was hybridization. So since both of these can use hybrid orbitals, that's the next thing I want to move on to is what it means to have hybrid orbitals and why we would hybridize orbitals. So hybrid orbitals are, I guess like the term sounds, a hybrid of these pure orbitals. So in molecules, rather than just individual atoms, oftentimes what we're going to see is bonds being made by the overlap of hybrid orbitals rather than pure s or p orbitals. The reason that we would hybridize orbitals is because we can really quickly see that the pure orbitals won't be consistent with the geometries of these molecules that we see. So let me give you a quick example of that. So let's take methane, CH4. CH4, carbon has a steric number of 4, so we know that that's a tetrahedral molecular geometry. And so we have carbon in the middle, we have 2 hydrogens here, and then one coming out at us, and one going back into the plane of the paper. We know that to be true based on what we've seen in the lab. And so if we think about how we would use pure s and p orbitals to get that arrangement, it's not entirely clear how we would do that. So if we imagine the s orbital here, I'll put the nucleus in green in the middle. And then I've got my px. Sorry, I guess this would be py. Here I have just 3 p orbitals in the same orientation, but of course we'll have px, py, pz, but we don't really need to worry about that when we hybridize them, and you'll see why in just a minute. So we'll have our py, then we'll have our px, and then I guess I could do a dotted line and a bolded one here maybe, and our pz. And remember that all of these p orbitals are orthogonal to one another, so they're all making 90-degree angles. So if we were using pure s and p orbitals, you can imagine that the way they're oriented now would give us an arrangement that would have 90-degree bond angles, and we know that what we actually observe is bond angles, 4 equivalent bond angles of 109.5. And so the way we reconcile this, and then I guess there is one other kind of perspective here as to why we would do this. You have an s orbital, which is lower in energy than your p orbitals because of the fact that it's spherical, so the electrons on average are closer to the nucleus compared to p orbitals. And then we have our 3 p orbitals. So if we're following the rules of when we do electron configurations, where we start at the lower energy orbitals and we don't pair things until we run out of space in that lowest energy orbital, and then when everything's filled up, we can move up to the next energy level and so on. Aufbau, Hund's rule, whatever the applicable rules are here. I think most of you probably know what I'm talking about. If we do that, and so we look at carbon has 4 valence electrons. Oops. Just look like carbon on its own, it's got 4 valence electrons. Then how I would depict that on these orbitals down here would be 1, then I would fill up rather than go up to the next energy level, 1, 2, and then 3, and then I don't pair them until I have to, until I run out of that energy level. So I put 1 here and 1 here. So if you think about that in terms of forming a bond with hydrogen, so let's take a look at hydrogen, which we have 4 of them, just write times 4. 4 hydrogen atoms with their own 1 electron. So I can only add electrons to orbitals that aren't currently full, which means I could put one of those electrons from hydrogen, let's put it in purple so we have some color coding, 1 here, and then I could put 1 here. And now it's not really clear how I could put 2 of hydrogen's electrons there in carbon's empty orbital. So that one's a little bit strange as well. And so what's the theory is that these orbitals can hybridize in order to properly form bonds in a way that's consistent with the geometries we see. So what would happen is if I were to take an s orbital and 3 p orbitals and hybridize them together, we always conserve the number of orbitals. So if I put 4 pure orbitals in and I hybridize them, I need to get 4 hybrid orbitals out. Before I keep going with that exact description, let me give you sort of a stupid way to think about what's happening when you hybridize orbitals. Certainly not anything physically or scientifically accurate, but it gives you kind of a better way to envision what's going on here. So let's just first start by saying that we're going to hybridize. If we hybridize all 4 of these, then what we're going to get out is 4 hybrid orbitals. sp3, and that sp3 notation, that superscript of 3 is really just saying that this is an orbital that contains both s character and p character, and the proportions of each is that it's going to be 25% s and 75% p character. That's what the sp3 means. So s, it's assumed there's a 1. So what it's saying is there's like a 3 to 1 sort of ratio of s character to p character. I should say, if this sums up to 4, a better way to say this is 3 out of 4, 3/4 p character, and 1/4 s character. That's mathematically the better way to describe that. So that's how you could view that. We don't put the 1 superscript, but that's sort of what this is telling us. Ultimately, it's telling us that we have 25% s character, 75% p. If you think about this is similar to like what we did with resonance hybrid, it just means that it looks more like a p orbital than it does an s orbital. That's what I mean by s character and p character. And I'll kind of show you using the cartoons how that actually looks. But let's keep going with what I was going to talk about. So if I have, let's do it this way. I have 1 salt shaker. It's a really stupid way of describing this, but I think it's really helpful to see why we're getting 4 orbitals back out and what the hybridization sort of means. Okay, so if I have, let's see, 1 salt shaker and 3 pepper shakers, which works out well because they have the same letters as the hybrid, the names of the atomic orbitals. So if I have 1 salt shaker, 3 pepper shakers, and I dump them all out into a bowl. So I dump them all into this bowl, all 3 of these, just empty them out into this bowl. And then I mix it up, take a spoon, whatever it is I want to take, and mix the salt and pepper together. Now I'm going to have a salt and pepper mixture, which is whatever our percentage is. If I have 1 salt shaker and 3 pepper shakers, then this mixture is going to be composed of 25% salt and 75% pepper. So now I have my empty shakers, and I'm going to fill them all back up. I'm going to take this mixture, and I'm going to refill those containers. So now I still have 4 containers, But when I dump that mixture in, I have 4 containers that contain a mixture of 25% salt and 75% pepper. So same here and same here. So while that's not scientifically particularly meaningful, I think it's a nice way of envisioning why is it when I have 4 atomic orbitals in, do I get 4 out? I take the contents of all 4 of these, I mix them together, and then I redistribute them back into those 4 containers. That's sort of how you can envision what's going on with orbital hybridization. Okay, so now let's see, where do we want to go from here? Okay, we're going to talk about orbital overlap and bonding, and for right now, I'm just going to tell you that the only way to make pi bonds, so we can make sigma bonds and pi bonds. I'm going to skip ahead to this just briefly because it's important in understanding why we may or may not hybridize orbitals. Whenever we make pi bonds, these need to be made of pure p orbitals. Actually, I just have it right here, so let's just highlight that. Pi bonds need to be made of pure p orbitals, always. And when you see the way that they overlap compared to sigma bonds, but out of necessity, you'll see why they need to be made of pure p orbitals. But we're not going to talk about that just yet. I want to, for right now, let's all accept that we need pure p orbitals anytime we want to make any form of a pi bond. And so if we need to make a pi bond in a structure, we need to set aside as many pure p orbitals as we need for however many pi bonds we need. If we don't have pure p orbitals, it won't be able to make pi bonds. So let's sort of commit that to our understanding now, and we'll address why exactly we need pure p orbitals in a little bit. Okay, so we looked at methane. I'm going to look at a case where we would want to do a hybridization like sp2 rather than sp3. So why did I want to do sp3 here, first of all? I wanted to do sp3 for methane because of it having a steric number of 4. So it has a steric number of 4 because it's bonded to 4 atoms, which means, and a much more ideal situation than what I was looking down at here, is that I could have 4 equivalent orbitals. If I had 4 equivalent orbitals, that means their energy they'd be at a degenerate energy level, which is meaning they're at the same energy level. So we would have 4 degenerate orbitals. That would give us a much nicer depiction of bonding than what we saw here. Because if we had 4 orbitals, let's do our s orbital here. P orbitals are a little bit higher in energy based on their proximity from to the nucleus. Our hybrid orbitals are going to be somewhere in between that energy level. So an sp3 hybrid orbital, for example, would be somewhere in between here. And if you look at sp3 versus sp2 versus sp, this has the most amount of s character. It's 50% s, 50% p. So you can imagine the energy of that would be closer to the S than any of those other ones. So it would basically look like this energetically. Let's just get rid of, we don't have to draw all 3. S orbital is the lowest in energy. Then the one that has the most S character, which would be SP. Then SP2. Then SP3. And then a pure P orbital. So if we're looking at this in terms of an energy scale, this is the lowest energy. This is the highest energy, so energy is going up there. And again, all these relative energies all have to do with proximity of the electrons to the nucleus. The closer they are to the nucleus, the more stable they're going to be. And so if we look at an s orbital, reminding ourselves that the nucleus is right here. The distance, the average distance of the electrons to the nucleus is this. For a p orbital, it's this, right? So it's longer. And then the hybrid orbitals, we can, obviously use a similar idea there for how close or how far they are. And I'll draw those out shortly. Okay, let's see, what else did I want to do? Okay, so I wanted to go to something that was sp2 hybridized. So let's take a look at a molecule called formaldehyde. Okay, so formaldehyde has a pi bond on it. So that tells me, just from what I said before, that pi bond is going to require that we reserve 1 pure p orbital. So let's take a look again at our 4 orbitals. We always have, for these second row elements, get rid of this, 1 s orbital and 3 p orbitals. If we're going to set aside a p orbital for a pi bond, then we're going to leave that one out of the mix. Or maybe what I can do is just redraw it down here, because I'm not going to hybridize it. I'm going to leave it alone. And then what I have remaining is an S and two p orbitals. So now imagine again back to the salt and pepper shakers. If I have one salt shaker, two pepper shakers, and I mix those up, that's going to be 66% pepper, 33% salt, and again I have three empty salt and pepper shakers to refill. So basically, I never poured the pepper out of this container. I only poured the salt and pepper out of these three, mixed them together, and poured them back into those three containers. Okay, so now what I have is three hybrid orbitals. I have sp2, 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 and then I have my pure p. So hopefully the salt and pepper shaker analogy helps understand why we get this certain number in and out. So this one pepper shaker here, we just never mixed it up. So we still have one pepper shaker that has only pepper in it. Then we took these three shakers, mixed them up, and poured them back into their containers. So now we have three with this ratio of S to P character. Okay, let's see how that is consistent with what we predicted just from this little shortcut table where he said the steric number of 4 equals, sp3, steric number of 2 is sp2, and so on. Here, let's look at the steric number. The steric number of this carbon atom is, we look at the lone pairs and the number of bonded atoms. Carbon here has no lone pairs. It's already surrounded by an octet, so there aren't any lone pairs on it, and it's bonded to 1, 2, 3 atoms. And remember, we don't care about how many bonds it has. We care about how many bonded atoms. Because these two bonds, being a sigma and a pi, they can't be separated from one another. They can't be separated in space or anything like that. They're all part of a system bonding the carbon and oxygen together. So that means we have 3 things that we want to space apart according to VSEPR. So steric number is 3. That tells us that the geometry to space those things apart optimally is trigonal planar. And it tells us that the hybridization about that carbon atom, the hybridization of the carbon, is sp2. So I told you from that little table, the correspondence of steric number here. It is steric number to hybridization. Now that's a shortcut, but the reason for that is, first of all, we set aside one pure p orbital for the pi bond, which means the sigma bonds we have in this structure, we've got 3 of them. 1, 2, 3. I could have highlighted either one of those bonds to oxygen. So if I have 3 sigma bonds, then instead I want 3 equivalent orbitals that I can use for bonding. And then the p orbital will sort of do its separate thing to form the pi bond. So that's why we get that hybridization, is because we need to set aside a pure p orbital for pi bonding. And when we do that, there's only an s and 2 p orbitals left. And so when we hybridize those to get out equivalent orbitals, we get 3 equivalent sp2 orbitals. Okay. Hopefully so far so good. What else do I want to say before I move on here? I think that's it for the hybridization. So now let's look at using hybrid orbitals to draw molecular orbitals in terms of drawing bonding and anti-bonding molecular orbitals. I guess actually one last thing I wanted to wrap up with here was how to actually draw these hybrid orbitals. So, okay, let's imagine to hybridize an orbital. So let's say we just take one s orbital and one p orbital to make an sp hybrid orbital. What you can imagine doing is taking the s orbital and overlapping it on one of these 2 lobes of the p orbital. And so then what you get is something that looks like this. And actually, let's draw a pure S over here for reference. You get something, the p orbital on the top has sort of a slightly larger lobe, right? Because I'm overlapping that S onto one of those 2 p orbitals. And if I were to overlap one s and 2 p orbitals, basically this shape is going to look more and more like a p orbital the more p character I have until it's completely pure p character. So now that I gave you sort of the idea behind what I'm doing, let me draw the other extreme and then kind of draw them going down towards the s orbital. So here's my p orbital. I'm going to exaggerate it just so I have room for actually showing the difference between these. I'm just giving myself a dotted line here. So this is S, this is P. Now I'm going to do sp3, which would look the most like a p orbital. What's going to happen there is it's just going to become a little more spherical in shape. And then as I go down to add even more S characters, so from SP3 to SP2, I probably should have exaggerated SP3 a little bit better. Sorry, just because I'm not going to have room to show the difference. Oops. So that's SP3. Then I'm going to go down to SP2. It's going to get even rounder. Move this over here. SP2 is going to look even rounder, so it's going to look something like, oops. And then even more here. So something like that. I'm not a great artist, but this is my my best depiction of how these look. So you can see that as you start from pure S spherical, and you work your way over to this pure P dumbbell shaped, you can see how the S's, they get, the ones with more S character are a little sort of wider and rounder, and then they slowly elongate as you get up to the pure P character. So this is S, SP, SP2, SP3, and then P. Now, granted, if I'm not drawing all of these orbitals one next to the other, then artistically, it really doesn't matter if you're attempting to draw an SP versus SP2 versus SP3. If it's out of context and it isn't next to another one, it's really going to be, you can't really tell one from the other. So I just basically just draw one of those lobes a little bit more exaggerated and a little rounder than a P orbital would be. So if I drew this, you'd have no way of looking at this and telling me if it's SP3, SP2, or SP. All you could really say is it's not P and it's not S. It's definitely a SP hybrid orbital. So I'm just letting you know artistically, it doesn't matter, exactly how those look, as long as you can tell that it's some form of a hybrid. If they're next to one another, just so you can visually see how they would differ from one another, that's what I've done here, just so you can actually see that transition from S to P. Okay, let's go over, okay, so now we're ready to start looking at orbital overlap and bonding. Okay, so sigma bonds are made by head-to-head overlap, and they're made typically of hybrid orbitals, but sigma bonds can be made of any kind of orbitals. We can overlap two pure S orbitals, two pure P orbitals in a sigma bond. We can do an SP hybrid orbital with an SP3 hybrid orbital to make a sigma bond. So sigma bonds can be made of head-to-head overlap of pretty much any kind of orbital, hybrid or pure. And the reason it's so flexible has to do with the way that sigma bonds overlap, or the way that the atomic orbitals overlap to form sigma bonds. So let's take a look at that. So here I decided on sp2 for some reason. So I'm making a sigma bond between two sp2 hybridized atoms. Doesn't matter what they are for right now. And it really wouldn't matter if I had written sp3 here, honestly, because you probably wouldn't be able to tell the difference unless it was next to something that was sp2. Okay, anyway, sp2. So it's going to look something like this. One of those lobes a little bit bigger and rounder, bigger than the other and a little rounder than they would be in a pure p orbital. And then I'm going to take another one like this. Actually, let me move this down here because I'm going to have to rotate them. So here are my two sp2 hybrid orbitals. What a head-to-head overlap is when we take the larger orbital of each one. So here, this larger orbital and this one here, and we combine them in phase. And we combine them in phase and, head-to-head. So head-to-head means we're going to put it on its side. The reason we do head-to-head overlap for sigma bonds is sort of similar to why the s orbital was shaped spherically, whereas p orbitals we had to change the shape. Sigma bond, and that was because the s orbitals are the first orbitals to be filled, so naturally they're going to be the ones that are the lowest energy or the best possible distance from the nucleus because of the first electrons we put in there. Similarly, a sigma bond is the first bond you form. A pi bond doesn't exist unless you already have a sigma bond, right? If a pi bond is the only bond there, then it's by definition not a pi bond, it's a sigma bond. So the sigma bond is the first bond we form between two things, which means that sigma bonds, the molecular orbital, the sigma bonding molecular orbitals are going to be made by overlapping the atomic orbitals in the most optimal way possible because it's the first time we're forming a bond between the two things. So the most optimal way to overlap these orbitals would be head-to-head. Let me draw on the nuclei so we can remember where that is. And by the way, the way I have them drawn at the bottom here is actually considered a side-by-side overlap, which is not what we do for a sigma bond. but it's actually this can actually help us to describe why we need pure p orbitals for a pi bond. But let's hold off for a second. Okay, let's see here. So let's go ahead and show the nuclei here. So I think it's important to keep that in mind when you see how these things combine. And then I'm going to shade them in a way that's suggesting an in-phase combination, which is two wave functions of the same sign, giving us constructive interference. Okay, so the reason we do the head-to-head overlap is this gives us optimal overlap between those two wave functions. So I can take this and I can drag it here. So remember, the thing I don't want to do is I can't overlap the nuclei with one another. What I want to do is bring the nuclei, overlap the shaded portions of the orbitals as best I can, ideally perfectly, without overlapping the nuclei. So it turns out here what I can do is I can drag this right here. I can effectively overlap those two shaded orbitals 100% before those two nuclei come into contact. And look at what that leads to when I combine them. Now all of that pink shaded region, all that electron density is exactly between the two nuclei. That's exactly what we're trying to achieve here when we form these molecular orbitals, particularly bonding molecular orbitals. So that is a perfectly ideal way to overlap those, and that's why sigma bonds do that. If it's the first bond that forms, it's going to do it in the best way possible, and this does it actually perfectly. So when I combine these in phase by doing this head-to-head overlap, so head-to-head is exactly what I'm seeing here, then my diagram looks pretty much exactly like what you just saw. Kind of looks like one of those little wrapped pieces of candy, with those two larger lobes overlapping, and then all this electron density here between the two. Okay, I'm just going to note right now that this is, copy and paste this because I think I can use that later. Right now I'm going to note that this is a side-by-side. So I'm going to cross them out and say that's not what I'm going to do. I'm going to do the head-to-head overlap. Okay, so before we get into any sort of pi bonding systems, let's now do the out-of-phase combination. So the out-of-phase combination is still going to be, just like we saw with the head-to-head. But now we can do the out-of-phase combination version of these two. So let me just go ahead and copy these, I suppose. And we are going to do our out-of-phase combination. I guess maybe I'll just get rid of this altogether right now. I don't need to keep it. But now I'm going to change the shading. Oops. So that now we're indicating them as being out of phase. So that means I need to make this one here. Okay. So now if I do it this way, now what I'm going to get, draw my two nuclei. As I bring these two together, right, what's going to happen is these wave functions on these two lobes that are not in phase with one another, as they come into contact with one another, they basically squash that wave. They cancel it out and make it zero. So as we bring these into proximity, just like we did the other ones, now those wave functions in the middle are basically canceling one another out. And so what's going to happen, the result is going to be in here, we're not going to have electron density shown, because as we bring those two together, the electron density cancels, they cancel each other out. So instead what we have is just stuff on the outside here. Let me draw the phasing like we had here. So I have the pink on the right hand side. And this would be my antibonding orbital. So sigma and sigma star. And again, we can see, why this isn't, why we might consider this to be anti-bonding in terms of an orbital. Is because there's no electron density between the two nuclei. The only place we have electron density, or the probability of finding electron density if it's in that orbital, is outside here, is completely outside of each atom, not between them at all. Let's see, what else do I want to say about this? Yeah, so another thing I want to bring up, because I think we started talking about in lecture what these orbitals and antibonding orbitals really are. Well, so that for the bonding orbitals, that if you have electrons in them, then again, like I said earlier, they're describing the probability based on the wave-like behavior of electrons and the wave function we use to describe their behavior. It's describing, when we square that wave function, we're describing the probability of finding an electron in a certain space. So you can see that wherever that orbital is larger, that's where there's a higher probability. So as we get closer to just a single nucleus, you'll notice how, let's see what color I'll use, this one. As we get closer to this nucleus, notice that line is going down. It's because we have a lower probability of finding an electron in that area. We find the highest probability of finding the electron here in that part where it's the largest. And that's because that's where it's, between those two nuclei. Great. And then for the antibonding orbital, if we were to have electrons in there, the probability of finding those would be that they'd be out here. And so you can see why that would amount to not facilitating bonding, because the electrons therefore wouldn't be there. So I like to think of this as, because a lot of the structures we're going to look at, although it's not exclusively like this, there are molecules that have electrons in both bonding and antibonding orbitals. But what it means is they definitely still have to have more in bonding than antibonding, or the bond wouldn't exist. So there are examples of molecules where they have electrons in antibonding orbitals, not enough to outweigh the number of electrons in bonding, but they can still have them there. Typically what we're looking at is this antibonding orbital being empty. And so instead of, it's not a thing that exists on a molecule. It's more so, if it's empty, a theoretical space in which placing electrons would lead to the weakening and ultimately breaking of that bond, should you actually equal out the number compared to bonding electrons. So I started talking about that with respect to acids and bases. So if I were to just go ahead and draw, let me draw one of an acid using these orbitals. So let's look at HCl. So chlorine has 3 lone pairs on it. So let's do the hybridizations of each of these. So chlorine has a steric number of 1, 2, 3, 4. So I was counting up the number of lone pairs and bonded atoms. That's why I'm circling the hydrogen, because it's a bonded atom. So chlorine is steric number of 4, a hybridization of sp3. Now let's do hydrogen. Hydrogen has, hydrogen we don't have to do, right? Hydrogen only has an s orbital, so it can't possibly have hybrid orbitals. And the steric number is always going to be 1, because it can only be bonded to one thing. So I guess H plus, you could in theory have a steric number of 0. But anyway, hydrogen is a pure 1s orbital. So let's go ahead and write that down. S orbital. So we have an s orbital on hydrogen combining with an sp3 orbital on chlorine. So what I'm going to do is look at the bonding molecular orbital between hydrogen and chlorine and the anti-bonding orbital between hydrogen and chlorine. So I have an s orbital for hydrogen that is like this, spherical in shape. And then I'm going to have an sp3. I'm going to draw something like this. And then I know that I'm going to do the head-to-head overlap, which means nothing really for the s orbital, but it means something for the p orbital, meaning I want to rotate it on its side so that larger orbital can overlap. So we have an s orbital, and I'm going to shade it. I don't have to, but I'm going to. But if I do shade it, then I have to shade the corresponding lobe that I'm overlapping with to show the bonding. So I'm going to do that. And those combine, and they're going to look basically something like this. And I'm going to go ahead and draw my green nuclei so I don't lose track of where that is. So I have my hydrogen nucleus here, my chlorine nucleus here. I'll label this as hydrogen. Okay. Hydrogen and chlorine. That's my bonding. Now let's look at the anti-bonding. So that is going to be pretty much the same, only I'm going to get rid of the shading. I'm going to phase it in the opposite direction. So now when I combine them out of phase, what I get is something like this. Like that. Shaded here, shaded here. I have this sort of minor lobe down here, which is the minor lobe, just means that smaller one. So I get something like this. So I have my bonding orbital, my sigma bonding orbital, and then my sigma star anti-bonding orbital here. So if I draw out HCl and actually superimpose this kind of drawing so we can see it, I would have my sigma bonding orbital right here. And then I guess I should have done this in a different color. So let me change this to purple, and then change this to purple. Now I'm going to superimpose my anti-bonding orbital, which looks basically like this. And that's sort of how they would all fit in. Now, chlorine has more going on than that. I'm not drawing all the orbitals for HCl. There's actually a few more, right? Because there are 3 sp3 hybridized orbitals that are housing these 3 pairs of electrons right here, here, and here. But usually what the purpose of these orbital diagrams is we single out and isolate and draw the ones that are relevant to what we're trying to answer. So what I was looking at in class is I was looking at if a base were to react with HCl. Let's take hydroxide. The base donates its electrons to the hydrogen of an acid. So hydroxide is going to donate its lone pair to the hydrogen of HCl. And because we know now that putting electrons into an antibonding orbital, if we put enough electron density in there, it will first of all weaken the bond. And if we put an equal amount of electrons in there compared to bonding, it will break the bond. And so what I was talking about there is it would make sense then, it would give the most efficient reaction is if OH donated those electrons specifically into where that antibonding orbital resides. Now, so for that purpose, I'm going to delete the orbital in pink because that was our bonding orbital. So yeah, it's still there, and yeah, there are lone pair orbitals to draw on chlorine as well that are no longer on this drawing. The only orbital I'm drawing is this one antibonding orbital between hydrogen and chlorine. But again, the reason for it is that's the only one that's relevant to the concept I'm trying to look at here. I'm trying to figure out how could hydroxide donate electrons into the antibonding orbital of HCl such that it could break the hydrogen-chlorine bond. Okay, so now let's think about OH and its orbitals. So I'm just going to look at one of the lone pairs on oxygen. Obviously, I have more than one. I'm not even going to bother with the hybridization. Let's just draw a quick and dirty version of an orbital lobe. I'm just going to draw something like that. So the lone pair on oxygen is going to donate its lone pair into this antibonding orbital of HCl. Now, why is it donating it? Why do I have it donating on the hydrogen rather than the chlorine? Because that's the atom it wants to bond to. If it were to donate to the chlorine atom, yes, it would donate electrons into this antibonding orbital, but chlorine doesn't want the electrons from oxygen. Oxygen doesn't want to give the electrons to chlorine. So that's not going to be a productive way of doing this, because that would require ultimately that the oxygen electrons came in here and then broke the bond this way. And that's not what we do. Remember, keep in mind what the reactivity is of an acid. The idea behind something being a strong acid, just do generically HA, is because you have a hydrogen that's bonded to an atom that is far more electronegative than it. Or for some other reason has a long bond and can stabilize a negative charge when it does leave. But anyway, let's just think about it in terms of a bond dipole for right now. A has a partial minus, which means the hydrogen has a partial plus. This bond dipole is the whole basis for why this thing is an acid, because it's got that hydrogen with a partial positive charge character, which then therefore reacts with electron-rich species, or typically bases. Okay, so OH isn't going to want to approach the side that's negatively charged. It's going to be repelled when it comes into proximity with chlorine. So yeah, there's an antibonding orbital lobe there, but hydroxide is just going to be repelled when it gets near there because chlorine's surrounded by electrons and is electron rich. Okay, so it could go there, but it's just going to bounce right back off through the repulsions between electrons. Instead, it could come around to this other side of this antibonding orbital, the one that's on the side of hydrogen, and it could overlap there. So let me just redraw this a little bit better. OH. And I'm going to draw again my orbital lobe on one of these. I'm going to draw it out like this. Okay, so if it wants to overlap with the antibonding orbital between hydrogen and chlorine and do so on the side of hydrogen, it would want to approach exactly here. So it would want to come in exactly this direction. It wouldn't want to come in this direction or this direction or this direction or anywhere on this side, because that means it's trying to form a bond with chlorine, which it won't want to do. It'll be repelled. Why does it want to come in exactly there? Because if I come in here, here, I can still overlap with that hydrogen orbital, right? But remember, think about this in terms of hydroxide. It's trying to form, I guess the reason is twofold. One, it's trying to form a new sigma bond to that hydrogen. And another one is it wants to maximally overlap with that antibonding lobe of hydrogen. And so if you think about this as a new overlap, just the same way we looked at those other ones, remember that a side-by-side overlap, something like this, if the OH were to look like this, and then coming from this trajectory, the side-by-side overlap isn't as efficient of an overlap. The most efficient way we can overlap these two orbitals is a head-to-head overlap. And so that's why the hydroxide wants to come in exactly from this trajectory, because then when it overlaps this orbital, it's going to make maximal amount of overlap with that antibonding orbital, which is going to give us the best way to weaken that hydrogen-chlorine bond. So just because this does relate to what we already got to, at least in lecture 2, about transition states, now OH isn't going to come in and be able to place 2 full electrons into the antibonding orbital all at once and then have that bond magically disappear. But what's going to happen is it's going to get into closer and closer proximity. So as this moves closer and there's a little bit of overlap, there's not a great way to draw this with an orbital diagram. But let's see, here's our sigma bonding and here's our sigma star antibonding. You can kind of, I guess, maybe imagine the lone pair on oxygen here. As it gets closer and closer to this sigma star, every time it gets a little bit closer, this bond starts to weaken. So when it's far away, it's a single bond. As that OH begins to approach and you get a little bit of overlap, we'll say that it's still mostly a single bond, but it's starting to break. And as I move this thing, as I move this OH orbital even closer and overlap even more, now that is going to become even less of a single bond. So now maybe it'll look like this. And then as that process continues, the HCl bond gets weaker as the OH bond gets stronger, and those two processes are sort of playing off of each other. Every time the OH donates into the antibonding, it makes the HCl bond a little weaker. That allows for the OH bond to become a little stronger. And the stronger that becomes, the weaker the HCl becomes, and eventually it breaks apart. So that's what we were looking at in terms of a transition state. So our mechanism for a reaction like this looks like this. The arrow pushing mechanism simply tells us from left to right, though, which electrons go where. So the hydroxide hits the hydrogen and the HCl bond breaks, and that gives us this. And while we're here, I'll point out, because people asked, you do not need to show the proper trajectory from which the base is approaching. If I ask for an arrow pushing mechanism, I'm not asking for any of this. These curvy arrows have no responsibility to show three-dimensional accurate trajectories from which things are approaching. There's no implication of that in a simple arrow pushing mechanism. The reason I'm showing it when I explain things like this is to explain why certain reactions are going to happen the way they do. But it's not because you have to show it that way in your arrow pushing mechanisms. That's why I specifically showed this not coming from the exact trajectory of my arrow, to show you that an arrow pushing mechanism has no requirement to show that. Okay, anyway, so the arrow pushing mechanism is this. That shows us where the electrons have to go to form those two products. But the transition state tells us what it looks like as bonds are being made and broken from the arrow pushing that's shown. So if I were to add a transition state into this mechanism, and also for a mechanism, you don't have to show the transition state. Transition states I usually won't have you draw. Again, it's another thing that's done for the purpose of having you understand why certain reactions work the way they do. So the transition state for this reaction, I'll just put it down here. Usually we put these in parentheses or in brackets. So as OH starts to donate its electrons to the hydrogen, OH is currently is a -1 charge before it reacts. As it begins to form a bond to hydrogen, which we'll include as a dotted bond, that means it's going to go down in charge a little bit. So it was fully -1. Now it's going to be somewhere less than 1. And so for that, I usually just include a partial minus. So not a full minus, partial minus. And then as it's starting to form a new bond to hydrogen, the bond between hydrogen and chlorine is going to start to break. And here we're going to put a partial minus because chlorine was neutral. When the bond fully breaks, it's minus. If I'm somewhere between 1 bond and 0 bonds, which is shown by this partial bond, then the charge should be somewhere between neutral and -1. And then the hydrogen in the middle doesn't have any formal charge because one bond has started to break, but a new one is starting to form, so that the net number of bonds around it is just still 1. So this is a little symbol people often use for a transition state. The transition state can help me explain certain reactions as we move forward, but aren't things I would typically have you draw. But again, it kind of shows you more the continuum of how this happens. It doesn't just automatically OH donates all the electrons into the hydrogen and the chlorine pops off just immediately. It will slowly approach, and when it approaches from a trajectory where you get ideal orbital overlap between the OH and the antibonding orbital of HCl, that's when you're going to start to see that weakening of that bond, and then that's when that reaction is going to continue that way. So as it collides over and over and over again, it's not going to be productive until it collides in a way where you start to get good overlap between those two orbitals. Let's see here. I guess I'll keep going a little bit more here just to show you at least what's going on with the p orbitals and why we need pure p orbitals for pi bonding. So again, sigma bonds can be made of pretty much any kind of orbitals, pure, hybrid, anything you want, because when you overlap them head to head, you can very easily get good overlap. And so it doesn't matter what the hybridization is. So let's take a look at what would happen if we tried to use hybrid orbitals in pi bonding. But I guess first what we should do is look at how pi bonds overlap compared to sigma bonds. So pi bonds are made of overlapping orbitals side by side rather than head to head. The reason for that is because the sigma bond, when we overlapped head to head, that put the electrons right here in the middle, which is ideal. If I were to overlap to make pi bonds in the same way, that means they would be occupying the exact same space, and we can't have these orbitals occupying the same space because we can only have 2 electrons in an orbital. So if you have 2 orbitals overlapping, then you're gonna break that rule. And those electrons repel one another, so we need them to occupy different spaces. So that's why we do side-by-side overlap for pi bonds, because if you imagine overlapping these side by side, first I'm gonna do, let's see, I'm gonna use a different color. So use pink up there. So I will use purple here for the pi bonds. So I'm going to do my in-phase combination first. I'm going to draw in my nuclei. When I bring those close together, what's going to happen for your in-phase combination is you're going to see something like this. Maybe I'll make them a little closer together. What color did I use? Purple. Okay. What I'm going to see when I combine them in phase, just by getting them as close as I can and overlapping them, so I'm going to form this thing sort of on the top and this one on the bottom. So remember, right here in the middle, I have no electron density. Like along that line, connecting the 2 nuclei. That's why you don't see anything right here in that space. But instead I get these two combining on the top and these two combining on the bottom, and I get something that looks like this. So this isn't as ideal as our sigma bond, right? Because these electrons were right in the middle of both of those nuclei. But in the pi bonded system, since we don't have that option anymore, the sigma electrons have taken that up, I'll still see that in general, the electron density is between the two nuclei if we consider it from sort of these dotted lines here. So they're still between the bounds of these vertical lines where the nuclei are. And that's the next best thing we could possibly have, because this section here is already occupied by the sigma bond. Now, I probably didn't make this good enough. The overlap will look nice here, but let me see if I can do it a little bit better. So if we move this up a little bit, you can see how you can overlap. Apparently I didn't separate them enough. I'm just freehand drawing here, so if I separate them a little better, you can see how you can actually superimpose a sigma bond and a pi bond, and they don't have to occupy the same space, right? So that's why we overlap the pi bonds side by side, because we don't have the option to do a head-to-head overlap anymore, because the sigma bonding electrons have already occupied that space. Okay, and then finally, anti-bonding. Actually, before we move on to anti-bonding, why do we use pure p orbitals rather than hybrid orbitals? That is because, and we don't use pure s orbitals because hydrogen is never going to form a pi bond, so that's not an option on the table. But why are they pure p orbitals rather than hybrid orbitals? Because remember, hybrid orbitals have this sort of weird shape to them, where one orbital lobe is a little bit larger than the other, right? Because you imagine superimposing a p orbital on top of an s orbital, so whichever lobe you put that on, that lobe is going to be bigger, the other one's going to be smaller. So because they're lopsided like this, if you try and do an in-phase combination like this, you're going to get a less than ideal distribution of electrons. You're going to have this big pink lobe up here, and then you're going to have this much smaller lobe down here. So that's not a very, even way to distribute the electrons, and therefore it's not a particularly stable way to form a pi bond by side overlap. And so if you want to form a pi bond, those are always done with pure p orbitals, and so they remain unhybridized in the event that you need a pi bond. Okay, so that's why we don't use hybrid orbitals for pi bonds. Okay, so we use pure p orbitals. Now we showed what the in-phase combination looks like. Now we can show the out-of-phase combination. So I'm going to draw two more p orbitals. Draw my nuclei in here. Now indicate them purple, as out-of-phase by changing the shading. And then what that's going to do is we're going to bring these in proximity to one another as whatever proximity we did for the sigma bonding and the pi bonding, because these are two nuclei, so I can't bring them into one proximity for this version versus its sigma bond, right? Like the two nuclei are going to be whatever distance they are, and then that proximity is going to define how well things overlap once it's there. Right, so the molecule they're informing these orbitals is going to kind of get into a proximity which is ideal across the board for the best way to overlap and form the lowest energy structure. Okay, so these, as we bring them close together, they're not going to get that close, and when they do, they're going to sort of, you can imagine them as kind of repelling one another. I know it's not necessarily mathematically the best way to describe this, but when I'm drawing these sort of cartoon diagrams of the orbitals, I kind of envision them as little magnets. Well, I guess a combination of magnets and balloons that can either repel or attract one another. Again, it has no real mathematical meaning, just like my hybrid orbitals with salt and pepper shakers was completely meaningless. This is likewise completely meaningless what I'm about to describe, but it's a nice way for me to remember kind of how to draw these orbitals. So if I imagine these as little magnetic like balloons, like those little clown balloons you can use to make balloon animals, if I look at these two, I bring these two balloons in close proximity, they are going to sort of attract one another, and I'm going to get one big filled balloon in the middle. If I combine these out of phase head to head, I imagine pushing these balloons close to one another because they're opposite in phasing. They repel one another like magnets, and they kind of force the air out of this side of the balloon into the other side as they come in close proximity. So that's kind of what you see here. Any of this make any physical sense? No, probably not, but it's a useful, I think, way to think about it. Same with the p orbitals. As they come into close proximity, these two balloon heads kind of attract one another and connect together. The bottom ones do the same thing, and when I bring them in proximity and they're out of phase, so repelling each other like, you know, two magnets, then they kind of force each other away, and they kind of, you know, bend out this way. Okay. Yeah. I think that's probably a good place to stop. There's probably one other thing we could take a look at, but I think I'll leave that for later. For now, we can stop here. And I really hope that this helps you better understand what's going on with this stuff. Even if you couldn't teach it to someone or, you know, draw out these diagrams without a good deal of effort, if you can just kind of generally understand the concept of what's going on here in terms of what molecular orbitals, bonding and antibonding molecular orbitals might look like, I just want you to be able to have some sense of what it means when I use these descriptions later on to describe why reactions work in a certain way or give a certain outcome. Okay, let's stop there.